we will continue with self-induction. First, I am going to remind you about electromagnetic induction. Then after, I will continue with self-induction. In electromagnetic induction, there was a coil and a bar magnet. There are two magnetic fields. One magnetic field is provided by bar magnet, which we said that it is an applied magnetic field. When we move this applied magnetic field, and this bar magnet closer or away from the coil, we make a change in magnetic flux in the coil. This change in magnetic flux induces an EMF, induces a current in the coil. And of course, every current has its own magnetic field, which is called induced magnetic field. Then when we are making them closer or farther away from the coil, we got a magnetic field in here called induced magnetic field. We got a current in here called induced current. We measure an EMF in here, which is called induced EMF. But we should make a change magnetic flux in here. But in self-induction, we are not going to use an external magnetic field. We are not going to use a bar magnet. So we will not use a bar magnet in self-induction. This is not going to be in our study. Only we will have a coil in self-induction. But this coil must produce an applied magnetic field. In here, applied magnetic field was the bar magnet, but applied magnetic field in self-induction will be provided by a battery. So we are going to connect this coil to a battery. So this is the battery symbol. One end is the positive terminal, this other one is negative terminal. And we know electric current is provided from positive terminal to negative terminal when we join them. But initially the switch is open. If switch is open, of course no electric current is provided. If no electric current is provided, there will be no magnetic field in the coil. So if there are no magnetic field, there is no magnetic field, there is no magnetic flux. So no current is provided because switch is open. No magnetic field is produced by the coil. So no magnetic field means no magnetic flux, because remember magnetic flux is A times B. If B is 0, magnetic flux is 0, A times B. You remember the question of magnetic flux? A times B. So first case, when switch is open, no external electric current flows in the coil. No current is given to the coil. If no current is given to the coil, no magnetic field is produced in the coil. So if there are no magnetic field, there is no magnetic field, no magnetic flux in the coil. So magnetic flux initially what? 0. After that, we are going to switch on the circuit. Close the switch. When the switch is closed, of course this time, battery will start providing electric current. So we know electric current starts from positive to negative. In this direction, an electric current is provided. I wrote in here external. So this electric current is provided by the battery. So of course there is an electric current in the coil from front to back. So by right hand rule, I can find direction of the magnetic field. If electric current is from front to back, forefinger is from front to back, right, the thumb shows magnetic field through the coil, which is from right to left. So these blue lines are representing magnetic field produced by the coil, but by using what? The battery. If no battery, this magnetic field cannot happen, it cannot occur. So this magnetic field, now the blue magnetic field, I am going to say applied magnetic field. Applied magnetic field. Provided by what? Battery. Without battery, can we do that? So this magnetic field is provided by battery. Now these blue lines are representing applied magnetic field because of the battery. Now question. Is there a change in magnetic field in the coil? Yes, it is. Initially it was 0. That increased to a maximum value if applied magnetic field through a coil increases. If applied magnetic field through a coil increases. Lenz law states that induced magnetic field must oppose this increase. Induced magnetic field must oppose this increase. Yani coil will react this increase. Coil will react this increase. How can it react? By producing an induced magnetic field in the opposite direction of this increasing applied magnetic field. So applied magnetic field is from right to left, correct? If coil will react this increase, induced magnetic field must be in the opposite direction of this magnetic field, according to Lenz law. So what's going to be the direction of the induced magnetic field? From left to right. These green lines now in here representing induced magnetic field of the coil. Yani blue are applied magnetic field. This is applied magnetic field provided by battery. Green lines are representing induced magnetic field. Induced magnetic field. Now, why are they in opposite direction? Because applied magnetic field is increasing from 0 to a maximum value. If applied magnetic field increases, Lenz law says that coil will react to this increase. How can it react this increase? By producing this magnetic field in the opposite direction. That's why this green and blue magnetic fields are opposite in direction. One of them is applied magnetic field because of the battery. Second one is induced magnetic field by the coil. There are two magnetic fields in here now produced by the coil. One of them is applied magnetic field, but coil used the battery. Second one is induced magnetic coil did itself. Both magnetic fields are provided by the coil. But remember electromagnetic induction? In electromagnetic induction, was it like this? No. Applied magnetic field was provided by the coil, by the magnet. Induced magnetic field provided by the coil. Yani single magnetic field provided by the coil now in electromagnetic induction. But in self-induction, what happened now? Both are produced by the coil. Because both magnetic fields are produced by the coil, this event is known as self-induction. Self-induction. Yani coil produces applied magnetic field itself, an increasing applied magnetic field it produces, then it reacts its own increasing applied magnetic field and produces an induced magnetic field. Okay, yes please.
Why they are in the opposite direction?
Because it's an increase. Magnetic field initially in the coil 0. Then increases to a number, is it? If something is 0 initially, which means it increases. According to Lenz law, coil reacts this increase, opposes this increase. How can we oppose an increase? By producing a magnetic field in opposite direction. That's why this induced magnetic field and applied magnetic field will be in opposite directions. Yes.
Teacher, in order to have induced magnetic field, we also need to have induced electric current, right?
Yes, right now I'll talk about this. So there are two magnetic fields. Of course, each magnetic field at the same time has a current. Current and magnetic field forms at the same time. Yes, this external current produces applied magnetic field. This induced magnetic field also must correspond to current. Because these two magnetic fields are opposite in direction, these two currents also must be opposite in direction. Yani induced current, which is green, I represent by green, and applied current by blue, I represent it by blue. They must be opposite in direction. Why? Because these two magnetic fields are opposite in directions. Because magnetic field and current directions are, if the current directions are opposite, magnetic field directions are also opposite. One of them is going up to the page, the other one going down the page, they are opposite in directions. If two physical quantities are opposite in direction, how can you calculate the total current? You subtract it. You should subtract that. Now you are going to subtract in this current from external current, you will calculate the total current of the circuit. So this opposite magnetic field, which is the induced magnetic field, comes from an opposing current on the coil called self-induced current. Sometimes it's called self-induced current to separate from electromagnetic induction, self-induction. Self-induced current. Yeah, this green current, sometimes called self-induced current. Total current in the circuit is calculated by subtraction of them. We will subtract them. Reason? Because they are opposite in directions. This phenomenon in physics is known as self-induction. Self-induction. However, this phenomenon, self-induction, occurs only a few milliseconds when you switch on the circuit. As soon as you switch on the circuit, as soon as you close the switch. Yeah, in this case. Now switch is closed, correct? As soon as you on it, you are going to observe it. Just milliseconds, not very long time. Because change in magnetic field happens, or change in electric current happens, only a millisecond from 0 to maximum value. After that, it is constant. After that, current becomes constant because this is a DC EMF source. DC EMF source electric current is always constant. Only from 0 to that maximum value, that jump. During that jump, you can observe self-induction. Then, electric current stays constant. If electric current is constant, applied magnetic field stays constant. If applied magnetic field is constant, can we talk about Lenz law? No, Lenz law is about change. So in this case, this green magnetic field disappears. Yani, this green magnetic field, which is self-induced magnetic field, appears only some milliseconds while we are switching on the circuit. Then disappears. Yes.
Teacher, will the induced electric current also disappear?
Yes, yes. And both this green magnetic field and green current disappears in some milliseconds. Only when you are switching on circuit you can observe these two magnetic fields. This green then disappears because electric current stays constant. If electric current stays constant, no change in current, no change in magnetic field, no change in magnetic flux, of course there will be no Lenz law according to this one. Yes?
When we open the...
Now we will open it. We'll talk about this. Okay, say that first you closed it, you produced these two magnetic fields, and of course after milliseconds, this green magnetic field will be lost. And only blue will remain. What would happen now if we open the switch? If you open the switch, this time electric current will decrease. If electric current decreases, magnetic field, applied magnetic field also decreases. Now, coil this time reacts this decrease. If coil reacts this decrease according to Lenz law, it must induce a magnetic field which is in the same direction of the applied magnetic field, of course. Now, I will explain that. A similar effect is observed in the coil if external electric current through the coil decreases by time by opening the switch. So in this case, these two magnetic fields will be in the same direction. These two magnetic fields, yani blue and green, will be this time in the same direction. Applied field, which is blue, and induced magnetic field, which is green, will be in the same direction. Why? Let me repeat again. When you open the switch, you cut electric current. No more current is given. If no current is given, current is decreasing. If current decreases, applied field also decreases. And so, coil reacts to this decrease. According to Lenz law, how can a coil react a decrease? By supporting it. This time, this green field supports the blue field. It comes in the same direction. If the fields are in the same direction, what about their currents? Also in the same direction. Get that? Green and blue currents are in the same direction. This also occurs some milliseconds while you are switching off. Only this time. 4 milliseconds, so this happens. Then everything becomes zero. That's why to observe self-induction, you have to switch on, off, on, off, on, off, on, off, on, off the circuit. While you are making on and off, you can observe self-induction. So, definition of self-induction. Every definition is a can be an initial exam question. This definition. The creation of an EMF in a coil due to variation of the current of the coil. Yani, this self-induction is because of what? Change in current. Variation means change. We are changing the current in the circuit. By making on, we increase the current. By making off, we decrease the current. So this variation of the current in the coil itself is called self-induction. Self-induction. Now, as I said, self-induction can be observed only if you make a change in electric current. We can change electric current by two ways. One of them I just showed you. Open and close the circuit. There is a second method. Second method is change or increase or decrease the electric current by using a rheostat. What is rheostat? Rheostat is a variable resistor. Variable resistor. Yeah, you can change the resistance of a circuit by using this rheostat. We know that resistance of a conductor is proportional to its length. I explained this in the classroom. As length of the conductor increases, resistance increases. As length decreases, resistance decreases. This rheostat is some conductors are wound on the surface of a cylinder, like this. Say that this is the wire, just like a coil, but coils are not so tight. These wires are so tight. So you wound it like this.
So it's a stretch coil?
Yeah, not stretched, compressed one. But coils are a bit different. They are very, very different materials. Coils are made of a different type of substance. These different types of substance. Okay, so there's a slide. You see, this is called slide. You can move this slide right and left. And when you are moving this slide, this is the diagram of the slide, electric current enters from this end and leaves from that end. Now, say that electric current is given. Follow the path of the electric current. It goes on like this, goes on by the wire and leaves from the slide. Now, length of the conductor is this. If you move this slide to the right, this time slide comes in here. Now length of the conductor increased. Follow. Electric comes in here, electric current. Follow these wires and leave it from here. By moving the slide back and forth, right and left, you are making change in the length of the conductor. As length changes, resistance also changes. Greater length, greater resistance. Smaller length, smaller resistance. If resistance of a circuit changes according to Ohm's law, what is Ohm's law? Because potential difference of EMF source is constant, then V is constant. If you increase the resistance by this variable resistor, electric current decreases. They reverse the proportion. While you decrease the resistance, electric current increases. Yani you are making a change in electric current by using this rheostat. Just move this slide right, left, right, left. While you are moving this slide right and left, you are making a change in the resistance, you are making a change in the electric current. And of course we know that if electric current changes, applied field also changes. Then coils start to react this applied field and produce a induced magnetic field and observe self-induction. Two methods we have for self-induction. One of them is use switch. On, off, on, off, on, off. One of them is the second one. Use a rheostat. By slide and moving the slide right and left, you make change in resistance, you make change in electric current. If electric current changes, of course, self-induction is observed.